Okay, good evening, everyone. Thank you for joining us this evening for what is our 30th year of Sea Secrets and our fourth speaker in this year's series. My name is Brian Soden. I'm a professor of atmospheric science here at the Rosenstiel School. I'll be your MC and host tonight. And before we get started, I'd like to thank our sponsors for the Sea Secrets seminar. We have our presenting sponsor, which is Norwegian Cruise Line, the Shepherd Broad Foundation, William J. Galloway III, Cheryl Gold, KB Life Enhancement Forum, the Key Biscayne Community Foundation, the Joan McMahon Family Foundation, Nicole and Myron Wang, and Southern Glazers Wine and Spirits. So thank you for all our sponsors for supporting this seminar series. We have really a world-renowned expert on a really fascinating topic for this evening's talk. But before we get to that, I'm going to continue our tradition of highlighting one of our exceptional alumni from the Rosenstiel School that will give a sort of a very brief presentation about a topic of relevance to tonight's talk. And tonight, I'm pleased to introduce Dr. Ryan Kramer. He will give a pre-recorded seminar, a very short presentation this evening. So Ryan is an alumni from the Rosenstiel School. He graduated in 2018, and I had the pleasure, actually, of being his Ph.D. advisor during his time here. After he graduated from the Rosenstiel School, he received a NASA postdoctoral fellow at the Goddard Space Flight Center in Washington, D.C. And after he completed that fellowship, he was a research scientist and still is currently a research scientist at NOAA's Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey. And that is one of the preeminent climate modeling laboratories in the world. And there at the laboratory, he does research to try to better understand the processes that influence changes in the energy flow into and out of the climate system and how that affects future changes in climate. Ryan works mostly from his office in Maryland. However, he's kind of, not only does he do research, but he also is a liaison between the climate modeling activities in Princeton with the satellite measurement activities that go on with NOAA and NASA there in Washington, D.C. So without further ado, we'll listen to Ryan's presentation.
Hi, Sea Secrets. I'm absolutely thrilled to be your opening act tonight and tell you about the type of work I do at NOAA's Geophysical Fluid Dynamics Lab and how it connects to the topic you'll hear about tonight from Dr. Hurrell on solar climate intervention techniques. So I spend my time trying to track and understand changes in Earth's global radiative energy budget using both observations and climate models. Earth's energy budget is really the fundamental driver of climate change. When the amount of energy coming into the planet from the sun is equal to the amount of energy going out of the planet, escaping back out to space, we have energy balance, and the climate is stable. But when something throws off that energy balance, like an increase in energy absorbing greenhouse gases, climate change occurs as a response and keeps occurring as the planet attempts to restore energy balance and restore equilibrium at some new, warmer climate state. And so this is where tonight's topic comes in. Scientists and engineers have been proposing methods to modify the amount of solar energy being absorbed by the planet versus the amount of energy escaping out to space, all in an attempt to reduce any growth in Earth's energy imbalance and slow down global climate change. There's still a lot of open questions about these methods, such as what exactly are all the climate impacts of these proposed methods? Should we therefore be implementing these methods in the future? All these questions that Jim is going to get into tonight. But importantly, continuing to monitor and understand changes in the global energy budget will be absolutely crucial to answering these questions and to tracking in understanding the effects of these mitigation efforts if we implement them in the future. Not just for solar climate intervention, but for any mitigation techniques, the energy budget, even before temperature change, will be the clearest and the first signal we get telling us whether those efforts are having the climate effect we intended or not. Fortunately, we've been measuring Earth's rate of energy imbalance. Since the early 2000s, NASA's Clouds and Earth Radiant Energy System series satellites have been flying around the globe, giving us measurements of Earth's net radiation. And we can use those measurements to understand more about why those changes are happening. So for example, we can average the data across the globe and we get this black curve here, showing us that over the past couple of decades, Earth's energy imbalance has been growing, a positive trend, meaning more heat uptake over time, leading to more accelerated global climate change. My job has been to try and understand exactly what's causing all of these changes and the overall trend in the imbalance. So, for example, I take a whole host of different satellite observations and decompose the total energy balance into contributions from key physical drivers. We can use satellite data to tell us the relative contribution of temperature change versus humidity change versus cloud changes to the overall energy budget. Each of these terms having their own rate of effect that either augments or dampens the changes in the total imbalance. This is really useful, but observations really can only get us so far. They can only tell us so much about what's causing the energy balance changes. So at GFDL, we develop and use climate models to further pinpoint the key drivers of the energy budget. For example, on the left, we use model simulations and observations to tell us what the relative contribution is of specific greenhouse gases on the energy budget, and not just their total contribution, but physically how they are contributing to the energy budget, what process they're contributing through. On the right, we do simulations of solar intervention techniques specifically. For example, testing the rate of response, the energy response we'd expect if we brighten marine clouds everywhere using sea salt injections. We do these experiments now so we can know what to look for in our observations in the future if we ever do implement these techniques. So myself and others essentially are working to build a framework allowing us to routinely evaluate and attribute changes in the global energy budget, starting with direct observations of the energy imbalance, using other satellite data to give a first order decomposition of what's causing those changes, and then bringing in modeling to further pinpoint what's causing the changes over time. All of this is really useful for answering the questions that Jim will talk about tonight and for monitoring climate and our mitigation efforts overall. And with that, have a great evening.
Thank you. Now it's my pleasure to introduce Dr. Jim Hurrell, our tonight's speaker. Jim holds the very prestigious position of the Scott Presidential Chair of Environmental Science and Engineering at Colorado State University. Prior to that, Jim was the director of the National Center for Atmospheric Research, which is one of, if not the most prestigious climate modeling center in the world. It's located in Boulder, Colorado. If anybody's ever been to Boulder, you see this beautiful building up on the front hills of the mountain, designed by IMP. That's the Climate Modeling Laboratory, National Center for Atmospheric Research. If you ever get to Boulder, you should definitely visit. They have a wonderful little museum in there and hiking trails up behind it. It's like an ideal place to work. And now, his time throughout his career, Jim has done research on virtually all aspects of climate and climate change and climate variability. He's received too many awards to really mention here tonight. He's been heavily involved with international projects like the World Climate Research Program, which is an international organization that prioritizes and coordinates research on climate throughout the world. He's also been heavily involved with the National Academy for Science and Engineering and Medicine, which is the preeminent scientific body within the United States. He's a fellow of the American Meteorological Society, the American Geophysical Union, the Royal Meteorological Society. He's really a big deal. So it's my pleasure to introduce Jim tonight and listen to a very important topic about climate intervention. Jim.
Thank you. Well, thank you very much for that very generous introduction, Brian. I hope I can meet your expectations after that introduction in this presentation tonight. And thank you, Ryan. That was a fantastic introduction to this topic. And so it's a pleasure, it's indeed an honor to be part of the Sea Secrets lecture series. I've been aware of it for quite some time. I've watched quite a few presentations via the archive on the internet, and it's just very nice to be here with all of you this evening. What I was asked to talk about is indeed a topic that you may be hearing about or reading about more and more in the news. Sometimes it's referred to as geoengineering, and it's fundamentally about the fact that we're experiencing climate change. Many of the impacts from climate change are very consequential. And is this something we should consider doing, maybe to avoid some of the worst impacts in the future? And so I hope to kind of take you through a journey of what some of the issues are related to this topic tonight. And I'm actually going to start off just with some very basic aspects that are exactly related to what Ryan just spoke of. And it very much relates to the overall Earth's energy budget. And when we think about the Earth's energy budget, we obviously get our energy from the sun. That solar radiation, about 30% of that solar radiation is reflected by the Earth and its atmosphere by things like clouds or tiny particles in the atmosphere, which we call aerosols, or maybe the land surface. One can think about like the polar ice caps as reflecting a lot of radiation. But most of that radiation, about 70% of that radiation, actually makes it all the way through its journey through the atmosphere and is absorbed by the land surface. Now, the Earth, like all bodies, if we had this room packed, it would eventually become kind of warm because we all emit long-wave radiation or infrared radiation, and the Earth is no different. So the Earth emits this long-wave radiation. Some of that radiation escapes to space, but some of it is absorbed in the atmosphere by what we call greenhouse gases. Greenhouse gases like carbon dioxide or methane. There's numerous greenhouse gases. And what those greenhouse gases do is then they re-radiate that radiation again in all directions. Some of that escapes to space, but some of it is redirected back down toward the planet. And that's what we refer to as the greenhouse effect. And we're very fortunate to be on this planet that we call Earth because we have, if you will, just the right amount of a greenhouse effect. If there were no greenhouse gases in the atmosphere, the planetary temperature would be below 0 degrees Fahrenheit. It'd be about -4 degrees Fahrenheit. But because we do have greenhouse gases in the atmosphere, the average temperature of the Earth, the average throughout the course of the year all around the planet, is about 59 degrees Fahrenheit. If we compared that to our neighboring planets, this is a picture of Mars. Mars has a very thin atmosphere. It essentially has no greenhouse effect. And the average surface temperature of Mars is about 80 degrees Fahrenheit below 0. On the other hand, our other neighbor in the solar system is Venus. Venus has a very dense atmosphere. The surface pressure of the atmosphere on Venus at the surface is about 90 times the pressure our atmosphere exerts on us here on the planet. And the Venetian atmosphere is 96.5% carbon dioxide, and that produces a surface temperature of about 843 degrees Fahrenheit. So Venus is actually the hottest planet in the solar system, warmer than Mercury, which of course is the closest planet to the sun. So the greenhouse effect is, thank goodness we have a greenhouse effect. We live on a wonderful planet that allows us to sustain this very nice optimum temperature that supports life in all of its forms. So what is the problem then? Well, this is really the problem of anthropogenic climate change. We know that greenhouse gases are increasing in the atmosphere, and they're not only increasing, but they're increasing very rapidly relative to natural rates of change. And we know that these changes are due to us, right? To human activities through the combustion of fossil fuels primarily, but also things like changes in land use, deforestation. And as I said, one of the real issues is not just that this is happening, but is how quickly it's happening. The rate of change is something that is very difficult for nature to keep up with. What it means, and if you think back to Ryan's talk, the addition of greenhouse gas molecules to the atmosphere simply means that more energy, more heat is being trapped in the Earth's system. So the question is not whether or not the climate will change, but much of the research that goes on here, much of the research that goes on in laboratories across the world trying to understand anthropogenic climate change is trying to better understand exactly what will those changes be, how will the Earth system be responding. One of the ways in which we measure this is at a NOAA observation site on the top of the Mauna Loa volcano in Hawaii. I'm not sure if you've ever been there, but just like Brian was talking about NCAR, you can go there and you can take a tour of this facility. And one of the things that they measure there is carbon dioxide concentrations in the atmosphere. These direct measurements started back in 1958. Carbon dioxide is very well mixed globally, so even measurements at a point location give a very good indication of what global concentrations are. And what you can see very easily in this curve is this steady upward trend, this increasing trend. Carbon dioxide concentrations have increased more than 50% since, say, the end of the 1800s, the 19th century. I was born in 1962. I'm 63 years old now, and carbon dioxide concentrations were 318 parts per million by volume the year I was born. So even in my lifetime, I've experienced this curve. We're now around 424 or 425 parts per million by volume. So we're increasing carbon dioxide considerably. If you put this into a longer-term perspective, this is what it looks like. We can also estimate what atmospheric greenhouse gas concentrations or carbon dioxide concentrations were like going well back in time. Here's the time series going back 800,000 years. And we do this by analyzing the air bubbles that are trapped in ice cores. Okay, and we can chemically analyze those and we can look at the CO2 levels. And what you really see on this slide is what we're experiencing in recent times is well outside the range of so-called natural variability. There are fluctuations in global CO2 concentrations due to changes in Sun-Earth orbital geometry. But if you look at this very rapid increase here near the end of the record, you can see just how dramatic that change has been. So we're fundamentally changing the climate system. There's a lot of different impacts from those added greenhouse gases in the atmosphere. And one of those that we often talk about and that you hear about on the news and read in the papers and magazines and whatnot is that averaged over the entire globe, we're seeing very clear evidence of a very pronounced warming trend. And that's evident here. These are measurements of temperature that go back to about 1850 or so, up through the most recent year, which is 2024 up here. You can see that there's a lot of variability because the climate system is highly variable in the same way that the weather can vary considerably from day to day. The climate system can vary significantly from year to year or decade to decade. But I think it's pretty convincing here that overall what we see is a warming trend that seems to be really accelerating and really increasing, and indeed producing record warmth in 2023 and 2024. The warmest years on record have all occurred, the 10 warmest years in the last decade, for instance. And so we know that the buildup of greenhouse gases is doing exactly what we would expect. It's trapping more energy in the system, and one impact of this is a warming of the planet. And the warming of the planet causes some issues, some challenges that we're faced with. It's stressing natural and human systems. And And if you look at the scientific literature and you look at reports that sort of assess this literature and our state of understanding, such as the IPCC, the Intergovernmental Panel on Climate Change reports that come out every 6 or 7 years, they've made very, very clear, convincing statements that the evidence shows that climate change is already causing a number of very catastrophic impacts across the world. And I won't read what's on the slide here. You can read that for yourself. And I think you're probably quite familiar with many of these impacts. And I think a really important point is that this is due to the, about 1.2 degrees of warming, this is what we've experienced to date. And every 1/10 of a degree of warming that we experience from this point on is going to make these impacts worse. It's going to really stress out both natural and human systems. And this is one of the reasons why a few years ago, in 2016, the nations of the world signed on to the so-called Paris Climate Agreement, where the nations of the world said, yes, we're experiencing climate change. If we continue to emit as many greenhouse gases, as much CO2 into the atmosphere as we are, we're going to suffer some pretty serious consequences moving forward. So what can we do as a global society to try to limit that future warming? So let's set some objectives, okay? Let's just set some objectives. What can we do? What sort of emission reductions would we need to achieve to limit the warming to maybe 1.5 degrees of Fahrenheit relative to pre-industrial times, or maybe at most 2 degrees of warming, so somewhere in this range. We should do everything that we can. The impacts are going to get worse, but let's try to avoid going much warmer than that. So what options do we have? How can we make Earth cool again, if you will? Okay? It's a relatively simple situation. We have two main options. Number one is what I think most of the researchers here and elsewhere would argue. The solution to climate change is to increase the amount of heat that radiates away from the planet back out to space, okay? This requires, quite simply, a reduction in the concentrations of greenhouse gases in the atmosphere, such as carbon dioxide. How are we going to do that? Okay? We can do that by reducing emissions. That's a really good start. And then I'm going to introduce an idea in just a moment called carbon dioxide removal. Okay? That's another form of climate intervention. So that's one thing we could do. The reality is this is what we have to do to solve the problem. But we're probably many, many, many decades away from seeing the benefits of doing that, because carbon dioxide has a very long lifetime in the atmosphere. We can stop emitting right now. CO2 levels aren't just going to drastically be reduced, so it's going to take some time. So that has stimulated more discussion around what I'm here to talk to you tonight about, and that is maybe we can figure out ways to reflect more sunlight away from the planet, and therefore avoid some of the worst impacts of climate change. This requires making the planet brighter, and there's several proposals to do that, as Ryan showed in one slide. And an attractive aspect of this idea is, unlike the long time scale that's associated with emission reductions, which again is what we have to do to solve this problem, maybe we could make the planet brighter and see some of the benefits of reducing the rate of warming or even leveling off the warming in a matter of just a couple of years. So that's what I want to take you through. So I've said multiple times already, the solution to climate change is reducing emissions. It's mitigation. That's how we solve the problem. That's how we cure this disease of a warming planet. And we have been making progress, and the United States has made progress. Emission levels have sort of leveled off. But the world as a whole is still increasing emissions. So global emissions of CO2 are still increasing. And in fact, if all the nations do what they pledged to do in the Paris Agreement, let's just imagine a world in which all the nations follow through and reduce emissions the way they pledged, we're still looking at something like roughly 3 degrees of warming relative to pre-industrial. That's almost 3 times the warming that we've experienced to date, okay? That's if all the nations do what they've promised to do. So what that means is that given this situation, right, given the fact that we're still continuing to increase emissions, this topic of climate intervention has come up. And the research community is recognizing that this is a very important topic. We have to understand what the feasibility, what the efficacy, what the risks, as well as the benefits of these approaches may be. So right now, I don't think the community is advocating at all for doing any of this or deploying any of these proposed techniques, but we need to do the research to understand it so that we can make informed decisions. So let me define this for you. This is the cover of a report from the Royal Society in the UK that came out in 2009. And it presented a definition of geoengineering. I'll explain why I have both climate intervention and geoengineering up there in just a moment. It defined geoengineering as the deliberate, and that's a very important word. This is something we would intentionally do. Large scale, we're trying to change the Earth's energy balance, as Ryan said. We're trying to affect the global climate system. Manipulation of the planetary environment to counteract some of the impacts or the effects of anthropogenic climate change. Now, about a decade ago, the US National Academy of Sciences, the National Research Council, did a study on some proposed climate intervention techniques. And there's a couple of studies shown down here, and I'll say more about those in a moment. But they chose the term climate intervention in place of geoengineering. The Academy felt that engineering sort of applied a level of control of this very complicated Earth system that we all love to study that was illusory. Whereas the word intervention means I'm going to try to do something here that I think is going to be beneficial, but I don't know exactly what the outcome is going to be, which is kind of a scary concept, okay? But, you know, we would do this hopefully to help the situation. So I personally prefer the term climate intervention. So let me talk, I'm here to talk about solar climate intervention or solar geoengineering, but I just want to say a couple of words, because I'm trying to paint the kind of the complete picture here, what the problem is, the buildup of greenhouse gases. We have to reduce that. One of the ways in which we can do that is to reduce emissions. And the other thing is through what we refer to as carbon dioxide removal. And I like this little cartoon of a bathtub. I think it tells the story pretty well. If you think about CO2 in the atmosphere being analogous to water in a bathtub, and we want to stop this water level from increasing, there's two things we can do. We can turn this spigot down, we can reduce emissions, okay? Or we could increase the amount of water that's draining from the tub. And this is essentially carbon dioxide removal. So if we turn the emissions down a little bit, but we don't increase these net removals, the water will continue to increase, and we don't want that. We have to do both of these things. We have to reduce emissions, and probably pretty dramatically. And we should also be researching ideas of how we can increase the amount of carbon that we're removing from the atmosphere and safely storing it or sequestering it or converting it into a useful product. So this is this 2015 report about carbon dioxide removal and reliable sequestration, the removal and long-term sequestration of CO2 from the atmosphere to reduce global warming. I'm not going to go through the details of these reports, but there was a more detailed report issued a few years later that kind of looked at the state of technologies and approaches and what we might be able to do and on what timescales we may be able to do it, that was published in 2019. And that focused primarily on land-based approaches, and I'll give some examples of those. And then this report in 2021, which looked at the ocean. Very relevant to the environment that I look out at the beautiful ocean in my day here, right? And can we enhance natural sinks, or can we use technology to enhance sinks of carbon in the global oceans? So again, I'm not going to talk about carbon dioxide removal. I'd be happy to talk with any of you afterwards if you're interested. But this is just an image from that 2019 report that I alluded to that talked about some technological solutions as well enhancing natural sinks of CO2 through things like afforestation. And this report goes through what we think the carbon removal potential of all of these different approaches may be. And there's a lot of uncertainties in carbon dioxide removal. So we have to reduce emissions. We're going to have to do carbon dioxide removal. But there's a lot of scientific uncertainties with this as well. How are we going to scale this up to really make a difference? And how can we scale these approaches up so that they don't cause more environmental harm than the good that would result from them as well? So this is really the key diagram for the rest of the talk that I'm going to give you tonight. I'm going to keep saying this. I know it's probably annoying. But to solve the problem, we have to reduce emissions. We're going to really have to think hard. There's going to be some sectors that are hard to reduce emissions, so we have to think about carbon dioxide removal. And we have to adapt to the climate change that we've already experienced, and we're going to have to continue to adapt to the extent we can to future climate changes. So if we do this, if we reduce this high emissions curve and we begin to bend this curve downward and reduce emissions, and we can remove carbon levels in the atmosphere even further through carbon dioxide removal, we're going to reach some point in time where, say, this is our temperature target of something like 2 degrees of warming. Let's say we want to limit the warming to 2 degrees, right? Eventually, as Ryan was saying, the system will come in equilibrium. The temperature can be 2 degrees when the amount of carbon dioxide in the atmosphere is at the right level to maintain that temperature at 2 degrees. But what do we do in the meantime? We're going to, if you will, overshoot this temperature target. We're going to go warmer than that because this is going to take decades to do. So should we consider something like sunlight reflection, solar climate intervention, to sort of shave the peak off of this curve and keep temperatures at this level until some point in the future we don't have to do solar climate intervention anymore? I think this is the primary way that many researchers think about this problem. So what are the major approaches? Ryan had a slide up that also showed things like we could maybe put mirrors in outer space and reflect sunlight, or we could brighten the surface by planting crops with higher albedos, or paint rooftops and roadways white. Excuse me. But the two approaches that are most often discussed in, excuse me, in the research literature right now is something called stratospheric aerosol injection, so putting these tiny particles, aerosols, well above the layer of the atmosphere in which weather occurs into a higher level called the stratosphere, about where your commercial aircraft sort of peak in altitude. Or trying to brighten, Ryan mentioned putting sea salt to brighten clouds, okay? So that the clouds have more water droplets, they essentially are brighter and reflecting sunlight that way, especially in portions of the ocean where there's clouds most of the year, like the stratostacks. If you've ever gone to Southern California, San Diego, you look out to the west and you see these low-level clouds. And that's the main idea on where you would do that. This is all based on aerosols. There's a lot of research here. Brian Soden introduced me. He's an expert on aerosols, many experts on aerosols here. Aerosols are a very complicated topic. He had very kind words to say about me, but I don't know very much about aerosols. It's really complicated, too hard. But I do know this. Aerosols have a net cooling effect. And not all aerosols cool, but in the net, aerosols cool the planet. And they do that two ways. One, by directly scattering sunlight back out to space. And the second, by indeed changing the characteristics of the clouds, perhaps making the clouds brighter. And these are the main ideas behind these two approaches. So marine cloud brightening, I'm not going to talk very much about this in my remaining time, but the idea, again, is to increase the reflectivity of clouds over the oceans where we have semi-permanent cloud decks. The analog is ship tracks. You're looking at a satellite photo here of the North Pacific Ocean, and you can see those streaks. They look like contrails from aircraft that fly around the planet, but this is not. These are the residuals of ships of opportunity that are traversing the oceans, and you can see that the particles that they emit as they're burning fuel can produce cloud condensation nuclei, and you can see these cloud streaks. So the idea is, could we add aerosols, maybe spray a fine mist of salt water that would produce more water droplets in the clouds and thereby brighten the clouds? These last 2 points are simply saying this is a really intriguing idea. This is a very important thing to study, and we are studying it. But this is a really difficult problem because we're still learning a lot about aerosols and impacts on clouds and cloud brightness. And our climate models, which are our laboratory, okay? It's how we study a lot of these processes and try to understand what the impacts might be on the climate, don't represent some of these processes that well. So what about stratospheric aerosol injection? Well, this is probably in this field of sort of solar climate intervention research, the most thought about, the longest, at least it's been thought about the longest, and maybe the best understood approach. And the idea is that maybe we could do something like a volcanic eruption. When a volcano goes off, a volcano like Mount Pinatubo, it puts aerosols into the upper atmosphere, and we see that it reduces planetary temperatures. And this is an example of that. This is a picture of Mount Pinatubo, the eruption. I know I'm getting old because I feel like Pinatubo just went off not that long ago, and it's 1991 that it went off, a long time ago now. But this is a trace of global temperatures in the lower atmosphere close to the surface. And you can see very clearly that there's a cooling impact from these aerosols in the atmosphere. And one of the reasons that it has this impact, if I can start this little movie, is here you'll see the volcano go off in June of 1991. And what you're looking at is not the movie. What you're looking at is a movie of the aerosols from the volcano and how they spread across the globe very, very quickly. And this is just from one volcano in the Philippines. So the idea is maybe we don't need to inject aerosols all over the place, maybe just a few key points, maybe 1 or 2 points in the northern hemisphere at lower latitudes and 1 or 2 points in the southern hemisphere, so that we have pretty equal coverage of aerosols that would be quite effective at reflecting sunlight away. So that's the idea behind this. And it's not a new idea. It's not some crazy idea that I or Brian Soden or Ben Kirkman or other researchers just came up with. It's been thought about for some time, right? It goes back, this is a very famous Soviet climatologist who, I think it was in 1974, published a paper back in 1974 saying, you know, I'm kind of worried about this climate change issue. Even before we had clear evidence that the planet was warming due to the buildup of greenhouse gases. We knew that would be the result. And so he's like, I'm not convinced that we can actually get the political willpower to reduce emissions. We might need to think of some alternative methods for maintaining global temperatures at safer levels. Wally Broecker, a very famous oceanographer, wrote on this topic in the 1980s. Tom Wigley was a colleague of mine at NCAR for a number of years. He wrote on it. But this guy here, his name's Paul Crutzen. Sadly, we lost Paul just a few years ago. He's a Nobel Peace Prize winning chemist, a very famous chemist, highly respected in the field. A lot of people thought this idea was just a wacky idea. It's a dangerous thing. We shouldn't even think about it. Until Paul Crutzen wrote an essay, which he called The Escape Route. And it essentially re-emphasized what these guys had been saying, that I'm not convinced that we're not going to need something like solar climate intervention in the future. And in my opinion, in my personal opinion, and I think a lot of colleagues agree with this, that really put a more serious light on this. People are like, if Paul Crutzen is thinking this, then maybe I should think about this a little more carefully. So we can model this. We can put this in a climate model, the same kind of climate models that we use to look at future changes in climate. And on the left here is a world with increasing greenhouse gases through the year 2100. And the orange curve will be what the global temperature does when averaged across the globe all the way up to the year 2100. And on the right is that exact same world, only now we have injected some aerosols, a little bit in the northern hemisphere, a little bit in the southern hemisphere, with the goal of keeping temperatures steady. Obviously, we didn't do this because in this model experiment, we started to inject these aerosols in the year 2020. But you can see that indeed, at least according to the model, we were able to sort of maintain global mean temperature. And you have a planet here where you have some cold patches and some warm patches. This is the natural climate variability. But the overall temperature stayed where we wanted it to stay. How am I doing here time-wise? 10 more minutes? Is that right? Yep. Okay. So we can look at other, I'm a scientist, so I have to show you a few nerdy sort of scientific plots, but this is a very simple diagram that the blue curve shows the world with stratospheric aerosol injection. The red or the pink curve shows the world with a climate change scenario. And here you're looking at overall temperatures over land regions. So if you just focus on the land. Now in this experiment, the stratospheric aerosol injection begins in 2035. And this is maybe a more policy relevant climate change scenario. And again, land temperatures basically stay at the level that we wanted them to, 2035. But you can also look at other things like extreme precipitation, the heaviest rainfall amounts. As the atmosphere warms, it can hold more moisture, so when it rains more on average, statistically across the globe. And you can see that there's a very significant increase in extreme precipitation events with climate change, and relatively little change. A lot of year-to-year variability, natural climate variability, but relatively little change in the average, which is given by the solid blue curve due to stratospheric aerosol injection. Now this is a really complicated diagram that I stated to Brian Soden and Amy Clement that I would never show this slide in this kind of a talk, and then I realized because the organizers of this wanted the slides a week in advance, and I was looking at them just before I came down here and go, oh my gosh, I have this slide. So let me try to explain just quickly what this slide is showing. So here we use something fancy that everyone's looking at these days, machine learning techniques, to ask a computer, if I give you a map of the future, could you tell me if you're looking at a world with stratospheric aerosol injection or without stratospheric aerosol injection? So let's look at a future state. Climate change is occurring. So it's a future state with climate change, and that's given by all of these little red or pink dots, and a world with stratospheric aerosol injection to try to keep temperatures near 2035 levels, and that's given by the blue dots. And where the computer has no skill, it's just flipping a coin. It can't tell. It's like, I don't know. I don't know if I'm sampling a climate change world or a world with stratospheric aerosol injection. That's sort of this gray region. And we ask, can you tell this future world, does it look any different than today's world? That's the question that we asked. So where it can't really tell the difference between the future world and today's climate, that's in this gray area. And you see for some variables, like precipitation variables, like I showed, heavy precipitation and the like, it can't really tell. In that sense, stratospheric aerosol injection is doing its job. It's preserving today's climate. But there's a whole bunch of other variables on this, and things like Arctic sea ice and soil moisture and surface temperature annual maxima. And in almost all of these variables, you can see that the blue dots are below the red dots, so it's more like today's world. But the computer is still pretty accurate in saying, yeah, it's more like today's world, but I can still tell it's not today's world. And that is because even if we do stratospheric aerosol injection, okay, things will change. It's a different forcing on the climate system. Maybe regional patterns might change, and the computer can identify that and say it's not the same. There are some variables, like the ocean pH, the acidification of the oceans, the stratospheric aerosol injection would not help with at all, because you're still got excess carbon dioxide in the atmosphere. The acidity of the oceans is still going to change in the same way, and so these dots are right next to each other. So the point is that stratospheric aerosol injection is not perfect. Even if we can maintain temperatures, there can still be changes in the climate, although we think, based on these model experiments, the future climate would look more like today's world than without stratospheric aerosol injection. We can look at other variables too, like Arctic permafrost, okay? So again, the blue is a world with stratospheric aerosol injection. This is the extent of permafrost in the Arctic. If permafrost melts, it has the potential to release enormous quantities of greenhouse gases into the atmosphere. So we'd like to stop this melt from occurring. This is volume, the volume of permafrost. And this is the permafrost temperature, the temperature below the surface where the permafrost is. And you can see under the climate change scenarios, we lose a lot of volume, we lose a lot of extent, the temperature continues to warm. But even with stratospheric aerosol injection, we continue to lose some extent and we continue to lose some volume. And that's because below the surface, where this warming has already taken place, where some of this extra energy has warmed permafrost temperatures, we will continue to experience permafrost melt, even if we do something like stratospheric aerosol injection, at least for the next several decades. And one final slide, some research that my group has been doing, and this is just a schematic, but if I explain this slide, this is the rate of temperature change, and this is something called the area exposed to climate speeds greater than 10 kilometers per year. What on earth does that mean? Okay, well, ecosystems, marine ecosystems, terrestrial ecosystems, can adapt to changing climate. The Earth has always had a changing climate due to natural variability. Some species don't adapt and they become extinct, but a lot of species adapt. But they can't adapt if the climate change is rapid, okay? If it's too rapid, the changes are too fast for ecosystems to adapt to. That's essentially what you're looking at. So if you look at this bottom bar, the kind of experiments that I've shown you, if we say maybe we want to keep global mean temperatures around 2035 values, what the results of this research are showing is that the climate speeds kind of stay in this very manageable range. This line would represent, if you will, what the natural climate variability is presented in the past. But if you do climate change, if you do climate warming, like we're currently experiencing, ecosystems are going to suffer. And I think we know this. We see evidence of this, right? But also what I want to point out in terms of stratospheric aerosol injection being, maybe a bad thing to do is that if we do it in such a way that we say, well, why would we just, Jim, why would you keep temperature at 1.5 or 2 degrees? If you can do this and you can cool the planet down, let's cool it back down. Let's cool it down to 1 degree or even 0 degrees of warming. If you do that, ecosystems are going to suffer just as much from a rapidly cooling climate as they will from a rapidly warming climate with climate change. And I just want to point that out. So there are still many, many unanswered questions. There's a growing amount of research going into this field right now. If we inject things in the atmosphere, what should we be injecting? If you inject sulfur dioxide, like volcanoes emit, and all these modeling studies have been done doing that, we know that it would have some detrimental impacts as well. Ozone recovery, we put all this effort into the Montreal Protocol, banned HFCs. The ozone hole is recovering. Minimum ozone levels are rising, so the ozone depletion is recovering. If you put sulfur dioxide in the lower stratosphere, it would slow that down a bit. It wouldn't stop it. Ozone would eventually recover, but it would have a negative impact. What would the regional impacts be? Most of what I've shown you are sort of global averages, but we don't live globally. You live in Miami. I live in Denver, right? What's going to happen in those locations? Still a lot of questions about that. And are there ways, if we're going to engineer the system, can we do it in such a way to minimize damage? Can we think of approaches to do that? A lot of questions. And then these questions are also huge. This last one, can it be governed? Can the world governments agree to come together and do something like this? But if they do, who gets to call the shots? Who gets to set the global thermostat? Who decides whether or not it should be at 1.5 or 2 degrees and things like that? So there's huge issues around the governance, as well as, is it even ethical to interfere with nature intentionally in this way? These are serious issues that the community, the broader research community is grappling with, not just physical climate system scientists. And there's some people, I want to point out, that are just vehemently opposed to this idea at all. There was this letter that was put out, an open letter, a few years ago, signed by about 400 researchers, who basically said, this is just a bad idea. We shouldn't even be researching this. If we start down the path of trying to legitimize this topic, we may end up doing it, and we may not want to do it. We're really nervous about this. Let's just kind of put a ban on the research. On the other hand, there's a lot of other researchers that say, no, right? I'm kind of freaked out about climate change. I'm really worried about climate change. I want to know if this is a tool that we have in our collective toolbox that could help us avoid some of the worst impacts of climate change, right? I want to know all the tools at my disposal to battle the immense challenges that climate change poses. This is Jim Hansen. Jim Hansen is a very famous climate scientist. He's the one who in 1988 testified before Congress about the risk that climate change was going to pose to the world. And I like to call this out because Jim, for his entire career, has been dedicated to understanding climate change and the impacts of climate change. And he has argued so strongly about the importance of reducing greenhouse gas emissions. But recently, like in a Science magazine article that I have quoted here, even Jim Hansen is saying, I don't know, I'm just not that optimistic about our ability to reduce emissions quick enough that we're going to avoid some of the worst impacts. We might have to consider something like solar climate intervention. The The National Academy of Sciences issued a report in 2021 that said the US should establish a research program in this area, but not advance a path for deployment, just try to understand. The American Meteorological Society has issued a policy statement urging for research on this topic. And this is a colleague of mine that was on this National Academy report, and I like his quote that he published in the conversation. Refusing to engage with solar geoengineering also raises questions. Can we be sure that we won't need it in the future? What if greenhouse gas warming generates horrendous climate impacts? Intolerable impacts. And if it turns out that solar geoengineering is not technically feasible or societally acceptable, shouldn't we learn that now? Shouldn't we be doing the research right now to understand what the benefits and the risks of this might be relative to the risks that we know climate change poses? So thank you very much for your attention and look forward to your questions.
Well, thank you, Jim, for a great talk on what I think is an absolutely fascinating topic, and offers maybe potentially some hope for avoiding the very worst consequences of climate change. Now, we have time for questions and comments from the audience.
One second.
Oh,
1 second.
okay.
I'll take over.
Okay. This is Jennifer Dillon, our Executive Director of Outreach.
Thank you. I always say this, I really appreciate your time. Thank you so much for coming and doing this, and I feel like I learned so much, and I'm on the weighing of the yes and no.
Yep.
I want to just say, if you would like to support Rosensteel, I'm going to put up my contact information here. You could support Sea Secrets. If you come to Sea Secrets and you like it and you're not a supporter, I encourage you to support Rosensteel. If you'll switch the next slide. I do want to mention before we get into the questions here, we have Giving Day coming up on April 3rd. But lucky for us, we can give early. Our early giving started like last week. So you can give anywhere. You can take out your phone, which I know that you said put your phone away, turn it off, but break it out now. Take a picture of that. It'll take you right to the site. And you can choose our scholarships or any other different area at the school. And we actually have some opportunities for one-to-one dollars for different scholarships and for our Rosensteel Fund. So if you haven't supported, this is the great opportunity to take advantage of our matching money that we have. And now I feel like I'm ready to break it over to you. Thank you.
Okay.
Get ready for your questions here. And I have our students. Where are they there? You got them. Okay, great. So what we're going to do is the students will come around through the audience. They'll hand you the microphone, ask your question, please. And we have some time we've got about, 3 or 4 minutes or so. We'll get some questions. And Dr. Hurrell said he will be here afterwards to answer any questions that don't get answered tonight.
Hi.
Yes, sir. Hi.
Very interesting. Thank you for your presentation.
Thank you.
Very enlightening. A couple of questions. Number one is, are you familiar with the work of Stephen Conning? He was Undersecretary in the Obama administration.
A little bit.
He wrote a book about, Unsettled actually is the book, about the difficulty of those climate models and how really, really difficult it is to make to make a decision based on measurements that are, very difficult to assess. That's number one. What do you make of this work, if you're familiar with? And number two, the worst case scenario. You develop the technology. What do you do when a military contractor shows up in your office and asks you for military application for this. I mean, if you say no, somebody out there in your change of command is gonna work, and that brings other risks. So,
I think I understand your second question. Let me address the first one first. I'm not going to comment on that specific body of work, but I will say that our laboratory for examining a lot of these questions right now is our climate models, right? And the exact same climate models that have been used to try to understand the climate system, to predict El Nino events, to predict future climate change, what climate change may be. We know anyone who works with these models knows that they're imperfect tools. The actual real world is amazingly complicated. It's very complex, right? There's all kinds of ocean processes and atmospheric processes and land processes and cryosphere processes interacting on all kinds of different space and time scales. We represent many of those processes quite well on these models, but some processes are represented less well than others. Some processes we may not even represent at all in some of these models. So what we do as researchers is we try to, as scientists, right, and like the IPCC assessments do, they not only assess what we know, but what we don't know and how we can narrow those uncertainties. So my feeling is that these climate models are extremely good tools. They're amazingly skillful at predicting a lot of the large-scale changes that we would expect from climate change. I teach a course on this at Colorado State University, and one of the things I like to do, I like to poke fun of my age, and I say I started my career as a postdoc at NCAR the year the very first IPCC assessment report came out. So let's look at what we said in that assessment report. Let's look at what climate models projected for the future. And now let's look at how the fidelity at which those climate models projected many, not all, but many of the changes that we have seen. So I think climate models are a wonderfully important tool that allow us to perform experiments where we can ask the what-if questions. What if we were to put aerosols in the atmosphere? What do we think? Do they have shortcomings? Absolutely. And we're working hard to try to improve those shortcomings all the time. Model development is a continuous exercise. Your second question, I think, relates to the fact of sometimes it's referred to as the slippery slope, that if we do this kind of research and we show that we could do these kind of deployments and pretty confident what the overall impacts on climate would be. Well, how are we going to develop the technology to deliver aerosols? Are we going to have high-flying aircraft that can dispense them? Are we going to use other technologies? And then the question is, what if we go down that slippery slope and then somebody says, okay, we've got this technology, we're going to do this. Or I think what you're asking is the risk of unilateral deployment. So all the simulations that I show kind of assume this world where the world is cooperating and we come together and we reach some sort of an international agreement and we're going to do this and this is what the temperature target. What's the risk of a rogue nation or a state or an individual actor doing something like this, especially if the technology is available? And I think that's a very real risk. I think if you talk with a lot of social scientists that think about these things, that look at the geopolitical landscape, some people feel that there's a real possibility that somewhere in the not too distant future, someone's going to try to do things like this. My argument is I want to do the research right now. I want to understand if someone does this, what the impacts are going to be. Because maybe the best way to prevent that kind of rogue action, not probably, I would argue strongly, the best way to do that is to do the research, to show what the risks, along with the benefits, but what the risks are. Maybe that's the best way to preclude that kind of action. So that would be my answer to that question.
Subtracting the human production of greenhouse gases, could we predict whether we are entering a glacial phase or an interglacial phase with the models we have?
Well, yeah, I mean, we have a pretty good understanding of Sun-Earth orbital geometry. If you take the human component out of the climate system and you go back to that 800,000-year history of CO2 that I showed you, what you see are peaks where CO2 concentrations are about 280 parts per million by volume, and then minima where they're about 180 parts per million by volume. Okay, we know that's due to the Sun-Earth orbital geometry, right?
But where are we right now?
Well, we're in a warm period right now, right? So if humans weren't on this planet interfering with the climate system the way we are, we would probably go into a cooling period. But we're not. The signals that we're imposing on the system are far outweighing that.
What I mean is, say, without human beings, would we be entering a warming period or a cooling period?
We're at a, so pre-industrial concentrations are about 280 parts per million, which is about the peak of the natural cycles. So from here, on the time scale of thousands or tens of thousands
we would be going
of years,
down.
we would be going into a cooling period. But we're not.
After we take this question here, this will be our last one. If you have more questions, you can stay after. Thank you.
Kudos on the graphics. I found it very understandable, except for the one that you should not have shown.
I know, I shouldn't have shown that one. And that's one of the few graphics I actually made myself, so.
And so you couldn't stand not to share it. But one question, two parts. I'm given to understand that climate modeling is very computer demanding and that it takes some of the biggest computers in the world to do the kind of job that generate the numbers that I saw you there. My question is, what computers generated that data? And the second part of that, I didn't hear, you may have said, but I didn't hear anything about international cooperation on this kinds of study.
Very good questions, yeah. So specifically, the simulations that I showed tonight, both times where I showed the movie loop of the world where we kept temperatures at 2020 values, and then some of the charts like I shouldn't have shown that I showed, where we did the stratospheric aerosol injection in 2035. In both instances, those simulations were done on computers at the National Center for Atmospheric Research, NCAR. So it's a very powerful computing system, but it's nowhere close to the world's most powerful computing system. So you can do these simulations. Climate model simulations take enormous amounts of computing power, indeed. But it depends on how you configure the model and what question you're asking and what the resolution of the model is and the like. But we could do these on a fairly standard supercomputer, if you will. Second question was international cooperation. So that's a very, very good question. So what I showed you very briefly in this talk was a statement from the American Meteorological Society and a study from the US National Academies of Sciences, which was established by President Lincoln to advise the government on matters of importance when it came to science and engineering and ultimately medicine. So all that report could do was advise the US government on what it should do. But if you look at that statement, it says we recommend in that study that the US, in partnership with nations across the world, in other words, work with nations across the world, put together a research program on this. Brian mentioned in his introduction, I've had the privilege of working with many international scientists through the World Meteorological Organization and one of their programs called the World Climate Research Program. The World Climate Research Program, just about a little more than a year ago, to show you this is a timely topic, established a new major activity on climate intervention. And what WCRP does is it draws scientists and governments from around the world that can fund that science together to tackle some of the most important problems that really need an international approach. So that international cooperation is definitely growing and being established. It's a global problem, just like climate change. So I'm happy to stay around and take any other questions. So thank you.
Thank you, everybody. We'll see you again on April 22nd for Jonathan Zawislak. Everything will be on Facebook and YouTube in the coming week.